last week's would be before.
So number 3.
I think it was quiz 2.
Number 2.
I think I gave you quiz 3.
Yeah, and I have half of those. And so you have just like 4 from quiz 2?
Yeah.
Okay. To this. Okay, so I want to push forward the exam to this Thursday, okay, instead of next Thursday. Hopefully you saw that. All right, there are several benefits to this. The first of which is it'll all be fresher in your mind. We have no problem finishing it, the material, Wednesday. So that's the first thing. The next benefit is that there'll be less material then. So if we push it out another week, there's plenty here we've talked about in the last month. Okay? And the final benefit would be that Friday we could just have off. No class, no recitation. So, you want to do this now?
Yes.
Okay. Both of us have extracurricular activities, so it's just easier if we just cancel class and cancel. No, but so the deal is that means you're gonna, with your weekend off, you work extra hard and do well in this exam. Okay, this is a really important exam because we've really kind of gotten halfway through calculus. Okay, this is this idea of accumulation from rate, starting with rate, building accumulation, is nearly half the deal. Okay, nearly half the deal. So you guys are doing it. This is the real stuff. This is calculus. Okay, so I put this concept review outline up, and it doesn't necessarily go in order chronologically, but it goes kind of by. So we've been building a process, and so it goes in the order of the process. So it's not exactly chronological, okay? So rate of change functions, step functions, constant rate of change, piecewise linear functions, accumulation function, and what we do today, integral, okay? So this is your task studying is, so basically you've got with studying there's 3, besides this outline, you have 3 resources, okay? You have, is this on? No. So the outline is kind of like the centerpiece of your studying, and then what you're doing is you're looking at videos, homework, and quizzes. This is what you got, okay? And you are going through this and finding all the examples and problems and things we talked about in the videos and the homework and quizzes that apply to any given bullet point, okay? So that's your task. This is kind of going in the order of the process, which is not exactly the order we built it up because we had to put the pieces in place to get the process, okay? But basically, you're looking for videos, homework, in the homework, and the quizzes for all these bullet points here that I've outlined, okay? So you need, if you didn't start kind of looking at this and start over the weekend, you need to start, you're not going to be able to start Wednesday night and succeed, okay? So it's been about a month since we started this stuff. So it basically starts with constant rate of change, linear functions up till now, okay? What else should I say about the exam? So I'm going to post blank versions of the quizzes, but I'm going to hold off on posting quiz solutions until after class Wednesday and allow you to turn in, if you want, you can turn in for a little extra credit, you can turn in quiz corrections, okay? So if you want to work on quizzes 2, 3, and 4. If you want to turn in corrections for some extra credit, now that's in addition to homework due Wednesday. So quizzes number 2 through 4. So that way, because I'd really rather have you dig in and think about and try to figure out what you did wrong rather than have the solution available, because having the solution available is good in a way, but then it also can be very bad in a way if you don't think, If you're just reading it and then saying, oh, I get it, then you probably don't, okay? So you got to dig in and figure this stuff out, and then once you've given it your best effort, which will be kind of on your corrections, then after class Wednesday, I'll post full solutions to those 3 quizzes, okay?
So we only do the ones that we missed then?
Yes, you could you're not redoing the whole quiz, just the problems that you missed, okay? Questions about studying for the exam or the quiz redos? Yes, sir?
Are there any graphing calculator questions on the exam?
I don't think so, but the file that we built to do the accumulation function, I mean, all of that stuff is on, all the mathematics behind it is on there. Does that make sense? Yeah, so I mean, yeah, that was kind of the result of all our hard work, and we're going to have the final conclusion today. Yeah?
I don't have quiz number 3. Did you pass it out?
Okay, so I still have, I think I passed them out to some of you and didn't finish. So if you want, you can come to my office today after 2:30 and I can give it to you. Or, let's see, when's your, or just make it, email me if that doesn't work out. But I'll be in my office today starting at 2:30 and you can get that quiz. Or if you want, after this class, you could follow me back to my office right after this class. And I could get the quizzes that I didn't pass back. And then he has number 2. He just has 4 or so left over quiz number 2s. And then I'm going to give you back quiz number 4 today. Okay, other questions? Okay, so this is not easy stuff. So you got to dig in, and if you can devote some time all 3 nights, Monday, Tuesday, and Wednesday night, to studying, that's going to be the best thing. Because it's not something you can just sit down in a couple hours and be ready for the exam. Okay, we've done a lot of hard stuff, and you've got to have it all clear in your mind. So, all right. So let's. So that outline, if you didn't discover it already, is posted on Blackboard in the quizzes and exams area. So there's that outline, and then Wednesday after class, I'll post the solutions to the quizzes 2, 3, and 4 in the same place right here. Okay, so we were looking at this last time, and you guys answered those questions again for your homework, so it should be very familiar with what we're looking at. We're looking at the red graph is the actual rate of change of weight. The blue graph is our approximating rate function, the step function, and that's based on the left sides of the intervals. And then over here, based on that step function, this is our accumulation function, the accumulation of weight over time. So, why did we do this all on graphing calculator? What was the point? What's that? What's faster? Okay, and what kind of thing are we wanting to calculate? What is our goal here? To get what did we want? What is our overall goal?
How much of a quantity we have?
That's right, Lauren.
We wanted to be able to calculate the amount of accumulation.
Okay, and how about this? Is this the amount of accumulation? It's estimates based on a good step function estimating or bad? Yeah, right? So this is okay, but it's not exact. It's based on these very large intervals of delta x. So what? Why did we do this all on graphing calculator? Lauren?
Because we're going to build on it and change a few values if we do. Pretty much makes it easier that way we can reuse same format of formulas.
Right, so, okay, that's true. That's yeah, so if we have a new rate function, we can just plug in the rate function, it'll graph all this stuff in an instant for us. Absolutely. Tell you.
Change the interval sizes too, so you can get more accurate.
Okay, so remember we said we made the delta x the slider, right? And this was the key to how powerful the graphing calculator was, because what? If I change the delta x, what will happen? So I'm going to change it from 0.5 to 0.25, say. What happened? Smaller intervals means what about the step function? Better, closer to the actual rate of change function. And now what about our accumulation function?
It's less abrupt.
What's that?
It's less abrupt.
Less abrupt. It's true. What's that? Yeah, it's more accurate, right? If the step function is a better representation of the actual rate function, then the accumulation function, which we build on that step function, will be better. So how about 0.1? So want to do this by hand? So how many from 0 to 2.5? That's 25 intervals. Want to do the accumulation by hand? No, right? But all we have to do is move the slider, and it'll do as many intervals as we want. So let me turn off. So here's 0.02. Now I'm going to turn off the actual rate function. Okay? The actual rate function is the blue one. I'm going to turn that off. Maybe. Where is it? Did I go right over it? Yeah. First one. I'm going to turn it off. What do you see now on the left? In the back. What does it look like back there? Does it look like a step function? No, it just, you can see it looks like the original function, right? But it's still a step function, just super small intervals. Okay? So how about this accumulation function? So this is the smallest I can do here is 0.05, 0.005. Okay? So a step function that has such a small interval that it's virtually the original rate graph and the corresponding accumulation function. And this is what we wanted. So the whole point is we wanted to build the actual accumulation function given the actual rate function. So turning on the rate, this is turning on the actual rate function again. They're like one and the same. And for that reason, so now my interval is 0.005. Is this the actual accumulation function? Talia?
It's not. It's really, really, really close.
Exactly. Okay, it's really, really, really close. Okay, so we basically just need delta x to be sufficiently small enough so it's sufficiently close enough. That's what we need. Okay, and maybe 0.005 in this case is plenty close. So we're plenty close to the something, I can't think of the word, but recreating. The step function has virtually recreated the original actual rate function, and so this is still a bunch of tiny little lines, right? It's still a bunch of tiny little lines, each at an interval of 0.005. But that's so small that that's virtually the same as what we can imagine as the actual accumulation function. Back to 0.5. So this is the kind of thing we did by hand. Right? This is the kind of thing we did by hand. We could come up with something, but not very accurate. So let's talk about... Yes, please.
So just to be clear, you would say that we put this all in graphing calculator just because it's faster and more accurate?
So basically, do you want to calculate, here's 0.025.
No.
Do you want to calculate this accumulation function by hand for an interval of 0.025. Yeah, so that's the real power of it. That I can just slide it in less than a second and have a very, very accurate accumulation function. Yeah. But also what Lauren said, now I can just come here and if I have a different rate function, I can just type in a different rate function and it'll graph the whole thing in an instant, right? Put any rate function I want in there and it'll give us the accumulation function because we wrote all the code based on R. So it's based on the rate function, the accumulation function that we wrote. So all we have to do is change R, and it gives us the corresponding accumulation function. Okay, so what we're talking about now is fine-tuning, right? Fine-tuning, getting the exact accumulation function. So here was our accumulation function, and by the way, for the exam, you got to know this inside and out. You got to know in the big picture what it's doing, and you got to know all the way down to what every detail, what every symbol means, okay? So we say when delta x is sufficiently small, we represent it as dx. This is really important. So what does this terminology dx mean? It's the same as a delta x, but just very, very small. You can think of it like the distance between electrons in an atom, okay? So this is really important notation. When you see that dx, it just means the same as a delta x that's super small as you can imagine. Okay, so that everywhere then that we have a delta x, we can, if delta x is very, very small, we can just replace it with dx. And in this case, basically we've created the actual accumulation function. So now with the actual accumulation function, this is very cumbersome notation. So there's a kind of a shorthand way of representing this. So this version of a of x is indistinguishable from the precise accumulation function associated with Rx. So we have simplified or shorthand notation for this, and this is what it is. Okay. So this thing and this thing are the same. Because this one is just this one with a super small delta x. And so in that case, where delta x is very, very small, we can write it this way. So now let's take a look at this and let's break down this notation. You really need to understand. So what do you see in here that you recognize? What's one thing that you see that you recognize? What's that? R of t. Marcus, what is it? You said you recognized it. What is it?
Don't remember, but I recognize it.
Is it R times t? You mean R times t? No. Sharon, what is it?
It's the rate.
This is our rate of change function, right? Actual or step function? Actual, right? If we have the actual accumulation functions based on the actual rate of change function. Okay, what's something else that you recognize? Tyler.
The a and the x from a to point x.
Okay, so A is starting value. And X is?
Where you're going to stop.
Exactly. It's the last, and this is key, all right? This is the last value of X. Or leftmost. Okay, what else do you see in this that's familiar or relates to what we were doing here?
It's the leftmost or the rightmost?
It could be either, okay? But it's the final value of X that you're going to accumulate to.
Accumulate to.
we're going to start at A, but it's so and this is a function of this, right? So that's what we were doing, accumulation function. So when the input into the accumulation function is where are we going to accumulate to, right? Where are we accumulating to? Okay, what else in this notation looks familiar? Yeah. Okay. So this is our very small delta x, right? Good. What did we say as in the very biggest picture of this accumulation function? What is this doing? What is it? What could you say? Equals sum of? Little bits of changes in y. What's another way to write that? Okay. Yeah, we don't have to put the. So that's the general idea, right? What, and how do we get those changes in y? Yeah.
Delta times k.
Yeah, and what was k? Yeah, so rate. Right? Because this was our constant rate of change on each step, constant rate of change. So, what about this? So really, in the biggest picture of this, they're just summing up a bunch of little bits of accumulation that we find using the rate, right? Rate times change gives us those little bits that we're summing up. See that here? Helios, what do you see? Where's that?
The RT is the k,
Right? The rate, okay?
and dt is the change in x.
Yeah, so it's this rate right here. See that? So sum of a bunch of r times delta x's. So this whole thing is what? Yeah, it's like a really, really small bit of accumulation. So if this was adding up a bunch of delta y's, then this is adding up a bunch of super small dy's, bits, right? dy equals r dx. Okay, and so then what letter does this look like right here? S. This is a German S. Stands for? Sum. So it really has, the same meaning as this. Summing up a bunch of little bits of accumulation, little delta y's. Summing up a bunch of little delta y's, starting at A and ending at whatever we put in for the input. That's what makes it a function. Our input's going to be how far do we want to accumulate to, and that'll be our final value. So everything in this relates to everything we built up in the accumulation function before. But now it's just our dx is atomically small. And we get the exact accumulation function. Amos?
Is that why we don't need to have the adding a little bit more at the end?
Yeah, so why don't we distinguish anymore between full intervals and a little bit more at the end? Right, it's so tiny that when you pick a spot, you're virtually it's so tiny that it's right. Yeah, I mean it's basically an infinite number of x values. So when you pick an x value, your interval is becoming kind of like almost like a point. So you've picked a point, and you're gonna accumulate up to that point. Should make sense. Does it make sense? Okay. All right. So here's a question. So it's a function of x. We know that's our x axis. Why do we have t rt dt here? David. What's that? Well, It might be, but our x quantity doesn't necessarily have to be time. Our x quantity could be something different. So like when we did the weight one, it was time. But we can accumulate other functions where the x value is not necessarily time. So any ideas? Why this new value t there? So it could be like u. So if we wanted, it could be, this could be r of u du, and there'd be this exact, it'd mean the exact same thing. Now it'd mean the exact same thing as, but why? So the question really is, why not x dx? Why not x dx? Rx dx. You want to try? Christina.
Well, maybe because you already have x as the last rate of change,
Okay.
so you don't want to plug it into that because you would just end up with the last point and not consider that starting value.
Rohit, did you hear what she said? Is that what you were going to say? Yeah, well, yeah, good. So if x is our final value, and we say we're going to accumulate up to 5, okay? So we want x to be 5. Well, then what will happen? We'll put r of 5, and will that be a function anymore? No, that'll just be the rate at 5. So it'll be like, instead of having the actual rate function, we'll just have a constant rate the whole way of whatever the rate was at 5. Does that make sense? Let me show you that. Okay, so any questions on this notation? Really important, okay? So, because this is basically what we've been working for a month and a half now, is to get the actual accumulation function. And this is how we notate it. So let's take a look.
So t then becomes your tiny intervals, your tiny changes. In
Right,
x.
right.
There.
Okay, so what do I want to turn on here? So in graphing calculator, it will graph. It has integral. Okay, that thing is called the integral, the German s. So what you do is, we can set up the accumulation function. We'll call it f of x, and you do Control Shift I. I thought Control Shift. What's going on? Yeah, Control Shift I. And so remember for our weight example, we started at 0. So we want to go to x. And then we had capital R was our rate. And so we'll do RT dt like we said in the... All right, and now I want to graph f of x. How do I graph f of x? Y equals f control 9x. But I want to graph it over on the right. So now I'm graphing the actual integral function. See that right there? I'm graphing from 0 to x, rt dt. So let's go back and make the steps big again and see what happens. So this was our first approximation using delta x of 0.5. And so what happens as we make delta x smaller? It's going to converge on the actual rate function. You can still see it's not at the 0.02. You can still see there's a little bit of a difference there. 0.05 is close enough that our eye can't really see the difference. Okay, so or close enough that the resolution of the graph is indistinguishable. Okay. So I'm going to turn off the approximating function. This is the approximating accumulation function. We'll turn that off. So I just have the graphing this capital F of x, which is our actual accumulation function, based on the interval 0 to x rt dt. So f of 2, what does f of 2 represent? Capital F of 2. What is that? What does that represent? Capital F of 2. So tell the person next to you. Think about it and talk to the person next to you. What does F of 2 represent?
Or whatever, 2. Okay, so this then becomes
Okay, DJ. What's up? Tell me.
We decided that it is the accumulation up to
The accumulation up to 2. So basically, F of 2 would be like plugging 2 into our function, which would be so this is how we say it, the integral from 0 to 2 of r. Am I going to put 2 in here? No, I'm going to leave it rt dt. Okay, so you said once more. What is it?
we said it was the accumulation up until 2.
The accumulation up to 2, or from starting at 0 and up to 2. Okay? How is it represented on the graphs? How is the accumulation up to 2 represented on the graphs? Go ahead. Y value of 2 on this graph. Is that what you're going to say, Tyler? Yeah, this is our accumulation graph. So, and notice if you put f of 2 in, it'll evaluate it for us, 4.93. So, there it is. 2, comma, 4.93. So now I'm going to change the function. So that means if we accumulate up to 2, the total accumulation of the quantity is 4.93, right? That's what the accumulation function tells us. Now I'm going to change the function and make this x and dx. Sorry. Here we go. Okay. So we're going to make this x and dx. And here's that point. To 4.93. When I change it to x dx, now what is it reporting the accumulation up to 2? 0.432. Okay? Not even close to 4.93. So, discuss with the person next to you. Why is it showing this value of 0.432 as the accumulation up to 2 when I change this to 0 to x, rx, dx? Go. Okay, Stanley, what do you think?
It just looks like it's taking the rate at 2
The rate at 2.
and then multiplying it by our incredibly small dx.
Okay.
And then
So when did it accumulate? What did it accumulate? What rate of change function did it accumulate? Yeah, Anthony.
It's taking the rate at the second interval.
Second interval. This is x equals 2, right? So it's like right here, x equals 2. So it's not the second interval. Yeah, Sharon.
Is it because it's only showing the change in y at that interval because you're multiplying by the rate for that interval, so it doesn't add the accumulation from the previous?
Kind of. So now this is the function the way we have it now. So if we plug 2 into this, what happens? It would be from 0 to what? R of 2 dx. So what is R of 2? So now all the way from 0 to 2, it's going to accumulate as if the rate was 2, like this. So what it just did, it just accumulated as if the rate was like this the whole way up to 2. So that's what happens if you do this. Your final value is going to be the rate over the whole interval. Whatever input you put in as the final value, it's going to take that rate to be the rate over the whole interval from 0 up to that, or from A up to that. So it accumulated at a much lower rate than actual the whole way, and therefore we got a much lower accumulation. You see? So what is the value of t? The value of t, it's still an x value, but it allows us to, if we choose our final value of x, then t allows, it's like, it's the bit by bit accumulation. It's the x value that allows us to still accumulate bit by bit up to the final x value. So we need a different letter. That t is taking on x values, but it has to take on all the x values from the starting point to the ending point. So it can add them up bit by bit. If you do this, all you're going to get is a constant rate over the whole thing of whatever the rate was at the end of the interval.
So then that graph, you don't have that graph, right?
What's that?
The f of x, with that constant rate over those 2-second intervals, like having that, you don't have that graph up with you.
No.
Okay.
So then T is at that point, you can use any letter besides X or Y.
Yeah, so here's the key. That this is, conventionally, our input is x. And so that's, for our accumulation functions, where we're going to stop accumulating. Then in here, you can use anything you want, but just don't use x. You see? So it could be like, R of b db. If you use x, that's what will mess it up, because you'll just end up with a constant rate all the way from A to the end. Whatever that rate is at the end will be a constant rate the whole way. But by using a different index or different parameter, then that allows us to actually get this bit by bit accumulation, starting at the lower and ending at wherever we accumulate to. Okay. So let's just go right to this. Why don't you just take a minute and each determine if it's valid, and then identify all the parts, describe the meaning of what the entire expression represents. Take a couple minutes with your partner to do this. I'm in the room. Oh.
have to say like, not, you have to see the FOX part of the forest to say it's not, but based on what he's telling us, how we
Is
don't have
it a valid, will we give you something that is important now? Because, like I said, we just have to create, we just make it, I'm still looking at the whole one.
So you said,
So 3 and 4 won't work. We need to get these close on the next.
How are you? How are you? Today? That's the same thing. Who are you, 10? Who are you, 10?
Okay, this is a rate that we have already.
Samantha. How are you, Sam?
Assign
Jen Rui.
value.
Well, paradox are
okay. You have to see, you have like S&T before it, and S&T equals, you have to see
so
it's like,
so what is talk about which those means?
well,
Remind me, I need to put a list on it. Tyler.
That is not okay. That's from
when you grasp the other one, it's still new, but it has brides. It's still being a graph, but the value that it gave was too small. Why is
It's
so it would be if we did that it would be
I mean, I think one would still be a constant rate. Because A is a constant.
Cool.
it does help kind of obvious
Caillou, Deng, Huey, Chen, Samantha. Okay, number one. Valid or not? Number one.
Invalid.
Invalid? Number one. Valid or invalid? Lauren.
At first I wanted to say that it was invalid until I realized that a sign of ETS could represent the rate function itself.
Okay, so the rate, she's saying the rate function is a sine e to the a. Agreed? Sure. Okay? And so then that times dA is, what does that represent? That rate function times dA represents? What's that?
the accumulation from 10 to 15.
No, just the a sine ea, not with this, without this. Just that thing, those things multiplied. What does that represent? Small change in y. Yeah, an itty bit of accumulation. It means an itty bit of accumulation, right? Because it's the rate times a little change in a. Or, our constant rate of change, delta y equals k delta x. Okay? And then we're going to sum up all those itty bits of accumulation from starting at a equals 10, ending at a equals 15. Totally valid. Totally valid. Okay, number two. Valid or invalid? Valid. What's f of t? Rate. Rate of change function. F of t times dt. Just a change in y?
Very small.
Very, very small change in y because it's multiplied times dt, right? Very small change in y, starting at 0 up to x. So this isn't a specific amount of accumulation. This has a value. This has a value. This is a function, right? It's a function of how far you're going to accumulate out to starting at 0. Right? Input is how far you're going to accumulate to. Number 3, valid or not? No, right? So it's going to end up, it's not going to end up doing what whoever wrote this, they're trying to do something, it's not going to do what they want it to do, right? Okay, this one, valid or not? Is it valid or not? Absolutely valid. Okay? The problem isn't having x's in here. What's the problem?
Not having your endpoint.
What's the real problem here? It's not just having x's to be your parameter inside the.
It's when you have X as the endpoint.
Yeah, it's when these match, right? It's when these match. That's the problem. When these match. Because you're not gonna get the function you want. You're just gonna get the rate at the end value for the whole interval from a to x. This is perfectly fine. If you're saying start at 2.1, accumulate up to 8, then x is perfectly fine. Last one, valid or invalid? Again, valid. Okay. What's our rate function? Rate function's in parentheses. Multiply that by dv, and you get very small change in y, or a little bit of accumulation. And we're going to start at 0 and accumulate up to x. So this is our accumulation function for this particular rate function. Okay, any questions on those? All right, so let's look at an example. Okay, so here's just a little summary. We think of this right here, a to x rt dt. It's the same thing as this that we've spent, all this time building up. It's the exact same thing with just an extremely small value of delta x. It's just a lot cleaner notation, right? It's just a lot shorter and easier, and it represents the actual accumulation function. Yeah?
So the second one you would use for larger changes in x, and then the first one you use for smaller?
This can represent any size. This can represent any size change. This has to be the very atomically small, like distance within an atom for those. And that gives us the actual rate, for the actual accumulation function. But this can be any size intervals. We can put, like I showed in the previous slide, we could put dx in here, dx, dx, and dx, and then they're the same. So this can be any size, and that's just for the super small. Okay, so rocket basketball. The rocket basketball, back to this problem, has a rate of change function of rx2x, and this time it's launched from a platform that's 95 feet from the ground. Okay, so remember back when we started the rocket basketball problem, that problem. Remember kind of what the framework was for that. Besides the fact that this is now starting 95 feet from the ground, what else is different now about this setup from when we did it? Do you recognize what's different? Okay, besides the fact that it starts 95 feet from the ground, besides that fact, what else is different about this? What's that?
The constant rate of change, 2x.
Is this a constant rate of change? 2x?
Well, that's the difference. They're saying that it's 2x. Instead of being like rate change 2, it's 2x, so 2 times whatever.
Was the rate of change 2 before what we had? Or what it was? What was our rate of change graph when we originally did the rocket basketball?
Delta F is equal to like
Increasing in steps.
Yeah, we said for the first half second it was 0. The next half second it was 1 feet per second.
But in between the jumps, it was constant. So in between each jump, it was specific.
So is this different from that, and how is this different? So this is what we worked on before when we started the basketball problem. Now we got 2x.
It'll be constantly changing instead of just jumping.
He said instead of jumping, now it'll be constantly changing. So let's put that in. So we'll go back to our, for the rate function, let's put in 2x. And we'll start it at 0.5, the way we had it, right? This was blue, this was purple. Remember this? Look familiar? So before we just flat out started with the step function, and then we built up this accumulation graph. Remember that? Well, now what we're saying is, let's have the rate of change function be this blue graph. If we were to build a step function on that blue graph, it might be the one that we started with, right? So that step function is a valid approximating step function for this y equals 2x. So to see the actual rate, or the actual accumulation function, uh-oh, disappeared. Make the steps really small, and we know that we get the actual accumulation function. And then we could actually graph that. Let's turn this one off. Let's graph the integral function. Oh, please don't pack up. Sorry. Do this example. Okay, so now I'm graphing the actual accumulation function by using integral, right? Integral is actual with a really, really small changes in x. So based on what we did Friday, so there's some questions here, but they're really very similar to the questions that we did on Friday with the accumulating weight problem that we did. Okay, so all this for your homework on Wednesday. Use graphing calculator. Okay, use graphing calculator just to graph the accumulation function using the Control-Shift-I to do an integral, just like I showed you. And then these questions are very similar to the ones that we answered with the weight function on Friday. All right, and so this will be what your homework is like. So I'll post the homework, and remember you can do your makeup, your corrections for the quiz. Also bring those in on Friday. All right, start studying for your exams soon.
Friday or Wednesday?
Wednesday. Everything I meant was Wednesday. Wednesday.
I missed one quiz. Am I able to do anything for that? Maybe
Hold on a second. Let me turn the video off.